I haven't got the exact homework problems up yet. Peter's checking the web because we did a little changing around from what I have. The Wednesday before Thanksgiving, we discussed the notion of a ring R being an integral domain. It's an important class of rings. And in fact, all the rings we're going to study from now on are going to be integral domains. So an integral domain has got the property that if A times B is equal to 0 in R, then either A is equal to 0 or B is equal to 0 in R. Namely, no product is 0 unless it's stupidly 0. It's multiplication of something by 0. So as examples of domains, we had the integers, we had polynomials over a field. If R is an integral domain, so is R of x. Polynomials over R. So we had many examples of domains. Non-examples are rings like Z mod 4Z, where 2 times 2 is equal to 0. But neither 2 or 2 is 0. And what we showed on Wednesday, for those of you who took a quick break, is associated to any integral domain is a natural field, which we could call the field of fractions. That contains R as a subring, and is somehow the smallest field that can contain R in the sense that all you've done is formally invert non-zero elements. And the way we define this field of fractions, just to recall this for you. Oh, Peter, do you have the homework? Why don't I put it up while everyone gets seated now that they've come out of the... Thanks. 11.1.1, 11.1.4, 11.1.5, 11.2.2, 11.2.5, and 11.2.11, part A. There we go. Thanks, Peter. Well done. Anyhow, the way we define the field of fractions, just to recall it for you, was F was defined as a set modulo an equivalence relation, and it was the set of all expressions of the form A over B, where B was not equal to 0 in R, and A was an arbitrary element in R. So that's what I mean by fractions. But you have to take the equivalence classes on that set, where you said that the fraction A over B was equivalent to the fraction A prime over B prime, if and only if AB prime was equal to A prime B in R. So if you constructed the field of fractions from the integers, you'd get the rational numbers, and you have to remember that 2/6 is the same rational number as 1/3, even though they'd look like different symbols here. So the last time what we showed on Wednesday, and it's a wonderful thing that's discussed in the last part of chapter 10 in the book, is that on this set of equivalence classes you can put an addition and a multiplication, and you embed R. R is embedded in F by taking A to the fraction A over 1, or the equivalence class of A over 1. And that gives inverses, because now the inverse, this has inverse the fraction 1 over A, if A is non-zero. You can only make a fraction where the denominator is non-zero. So this is just big enough set to contain the inverses, and you can do this for any domain, and we identified the field of fractions for these various domains. It's more of a convenience to know that the domain is sitting somewhere inside of a field. It's, as Peter would say, it increases your comfort level with the domain. So we're going to go on now and study some wonderful properties of domains related to factorization of elements in domains that are all intended to generalize the question of factorization of an integer into primes, one of the big theorems of classical arithmetic. Now, if we do factorization in the ring R, in the domain R equals Z, and you follow the way you prove unicity of prime factorization in Euclid, it starts off with the first property that we prove about the integers is the existence of a Euclidean algorithm. So that's the Euclidean algorithm which says that if you have two integers, a and b, with a less than b, or maybe the absolute value of a less than the absolute value of b, because they could be negative integers, then you can write b as a multiple of a plus a remainder term, where the remainder is a positive number which is less than the absolute value of a. So you can always take away a multiple of a from b to leave a term which is less than or equal to the absolute value of a. That's more or less obvious from the geometric description of the integers. So here would be b, here would be your smaller number a. You'd march out, and ma would be the last time you got something that was strictly less than b, and then m plus 1a would be here. And so the difference between ma and b, here's the remainder r, would be a number less than a. So you can't always divide in the integers, but you can approximately divide, leaving a difference which is smaller than the number you're dividing by. That's the principle of the Euclidean algorithm. And from the Euclidean algorithm, we deduced a number of consequences for the integers. And the first one was every ideal I, say not equal to 0, is principal and the generator generated by the smallest positive integer d, which is in it. So in any ideal which is non-zero, it contains both positive and negative integers. You find the smallest positive integer in it, then the ideal has to be multiples of d. Because if you had anything else in the ideal, say b in the ideal, and you wrote it as a multiple of d plus some remainder term, then since b is in the ideal, the multiple of d is in the ideal, the remainder has to be in the ideal, but the remainder is less than d, so it has to be 0. So that shows that anything in the ideal is a multiple of d. So that's the first thing we deduced. Second thing from that, which was quick, in particular, ideals generated by two elements are principal. In particular, the ideal I that's generated by two numbers a and b is a principal ideal, d, with d equal to ma plus nb. Because the ideal generated by two integers consists of all integers of this form. That has to be a principal ideal generated by something, by part 1. And consequently, whatever generates the ideal has this expression. And in fact, from that we can conclude that d is the greatest common divisor of a and b. First of all, it divides a and b because a is in the ideal generated by d. So a is a multiple of d. It divides b because b is in the ideal generated by d. So b is a multiple of d. And moreover, if you had anything dividing both a and b, it would have to divide d by this expression. Because if it divides a and b, it divides ma plus nb. So that shows that d is the greatest common divisor. It itself is divisible by anything that divides a and b. So that just comes from the fact that every ideal is principal, applying it to the ideal with two elements. You get the existence of the greatest common divisor. All right, that's the second thing we deduce from the Euclidean algorithm. And the third thing we deduce, and this is a nice thing that is in Euclid, if p is a prime and p divides a product, then either p divides a or p divides b. This is a symbol for divides. I'm not going to keep writing divides. If a prime divides a product, it must divide one of the factors. And the proof of this, it follows from part 2 proof. If p does not divide a, then the GCD of a and p is equal to 1, because the only divisors of p are 1 and p. So if p doesn't divide a, the largest divisor of both of these has to be 1, which means that 1 can be written by 2 as a multiple of a plus a multiple of p. And now multiply this by b, and you get that b is a multiple of a times b plus n times p times b. Now p divides the quantity ab, P certainly divides this because it's a multiple of P, so therefore P divides this sum, so B is divisible by P. But we needed this mysterious expression of 1 to be able to prove it. And we wouldn't, this is not obvious at all. We're going to have rings where this is false. So to prove that a prime which divides a product divides either of the factor, we needed this greatest common divisor. And the fourth thing we can deduce from this, I'm going to put it up here, is that every integer n has a unique factorization into primes. N is equal to, well, depending on its sign, P1, P2. These could be the same prime. They could, namely, the same prime could appear several times. But the key thing is not that it has a factorization. That's obvious, that you can just keep breaking an integer up into indivisible factors. But that the factors themselves are determined by the integer, that it has a unique factorization, is a powerful theorem about the integers. And the reason this follows from 3 is you prove this by induction. On the number of factors. And just to sketch it, I mean, suppose n were also equal to plus or minus q1 up to ql, and this thing was true for, and k was less than or equal to l, and this theorem was true for numbers that had less than k prime factors. Then you would say, well, look, p1 divides n, so it divides a product of primes. Well, it's easy to go from this theorem that if something divides a product, it has to divide a factor. So P1 divides Q1 times the rest. So it either divides Q1 or it divides the rest. If it divides Q1, it's equal to Q1. If it divides the rest, it has to divide one of these factors. So you conclude from 3 that P1 divides some Qi, which implies that P1 is equal to some Qi. And then dividing both sides by P1, we get a number with less than k prime factors, which has a unique prime factorization. But again, we needed this property 3, that if a prime divided a product, it divided one of the factors. So then use induction. Divide and use induction. So ultimately, we see that this unicity of factorization in the integers follows completely from the existence of this Euclidean algorithm. We deduce, first of all, that ideals are principal. From that, we deduce the existence of a GCD. From that, we deduce this theorem about primes. And finally, the unicity of factorization. They all follow from that. Now, what we're going to do is see when this thing holds for other rings. So if we can establish a property like the Euclidean algorithm from another ring, all these things are just formal ring theoretic properties. They have nothing to do with being integers. So let's see another example where we can get the exact same mileage out of this. Another ring R with a Euclidean algorithm is R the polynomials over a field, where this is a field. And then what we know for polynomials over a field, here we have the size of a number, its absolute value. So for a polynomial over a field, we have its degree. So we know that if given a g of x, it can be written as a multiple of f of x, q of x, I don't know, plus r of x, where the degree of r is less than the degree of f of x. That's just polynomial division. So that's our analog of the Euclidean algorithm, that any two polynomials, if you're given g and f, it's not always the case that f divides g, but it can be divided into g in a way that leaves a polynomial whose degree is smaller. just like it can be divided into b in a way that leaves an integer which is, in some sense, smaller than your original integer you're dividing by. All right? And now I can deduce 1, 2, 3, and 4. One is that every ideal is principal generated by the d of x of least degree in I. Same proof. 2, any two polynomials f and g have a greatest common divisor, namely a polynomial d of x, which generates the ideal generated by the two polynomials f and g, because there's just a particular example of that thing. And moreover, this greatest common divisor can be written as a multiple of f of x plus another multiple of g of x in the polynomial ring. Same proof, because these are the elements of that ideal. So this follows. Now, to talk about what 3 is, we have to say what a prime is. So we say p of x is a prime polynomial, or what's usually used in the literature, irreducible polynomial, if any factorization p of x is equal to p1 of x, p2 of x, has degree p1 equal to 0. Namely, the only way you can factor it is to pull out a constant times a polynomial of the same degree. You can always do that, right? So that the only factors of p of x are either polynomials of degree 0 or polynomials of degree equal to p of x. No smaller factors. And then it implies that if you have two polynomials a and p, the GCD of a of x and p of x, the ideal generated by a of x and p of x is either equal to the ideal 1 or the ideal generated by p of x. Because if you have a polynomial that divides p of x, it either generates the same ideal as p of x or it generates the unit ideal. These are the things that generate. So p1 here would generate the unit ideal. And p2 would generate the same ideal as p. So the only possible divisors of p of x are 1 and p. And so if p of x divides a of x, the GCD is this ideal. And if it doesn't, the GCD is the ideal 1. And in particular, you can write the constant 1 as a multiple of a plus a multiple of p in the first case. And that shows, so if p divides a product of two polynomials, it must divide one of them. Exactly the same proof as in the integers. And 4, we conclude that any f of x can be written as a constant times prime polynomials. Has a unique factorization into primes. Now again, unique is only up to units in the ring. You can always multiply a factorization by a unit in the ring. And in this ring, the unit group is the non-zero elements of the field, the polynomials of degree 0. Those are the polynomials that are invertible in the ring. In this case, the ring Z, the unit group, was just plus or minus 1, and the factorizations were unique up to this changing by sign. But you get exactly the same structure for the ring of polynomials over a field. These ideals are very simple. You have a GCD, you have unique factorization into irreducible polynomials, as you did for the integers, and the key thing was the existence of this algorithm. So we could try to abstract that algorithm a bit and try to see, anytime we have that algorithm, all this stuff is going to work. So what would be a general Euclidean algorithm for a ring R? Well, we need a size function that tells us how large things are in R. A ring is Euclidean. well, actually a domain, always a domain, everything now is a domain, is Euclidean if and only if there is a size function. Let's call it, I forget what the book calls it. I'll call it delta. I'll call it delta. From the elements of the ring, which are non-zero, to the positive integers, so each element of the ring has some size such that for any a and b not equal to 0 in R, we have b is some multiple of a plus a remainder term with the size of the remainder being less than, with either, r equals 0 or the size of the remainder being strictly less than the size of a. So if we can do an approximate division and decrease the size of the element that we're dividing by, we call it a Euclidean ring, after the Euclidean algorithm in the integers. So for the integers, the size function is the absolute value of a. Okay? We've decreased that absolute value by r. For the polynomials, the size function of a polynomial is the degree of f, which for a non-zero polynomial is I think I need 0 here, huh? Sorry. Let's go 0. I apologize. You could have 0. In fact, we're going to find that delta of an element r is equal to 0 in these rings when r is a unit. The units are exactly the elements where the size function is 0. So here, the size, whoops. Maybe I want to exponentiate this size. No. Getting a little confused here. Delta of a unit should be 1. Yeah, exactly. Delta of a unit should be 1. The degree of a... Pardon?
Definitely should be 1 for you.
Yeah.
You add 1 to the degree of f.
Yeah, maybe I should add 1 to the degree of this. Degree of f plus 1. That's better. I think that'll do it. That's the same. Yeah, sorry, thanks. I don't want 0 to be in here. There we go. Delta r is equal to 1. R is a unit. I mean, for the absolute value of an integer, I want it to be, this is plus or minus 1 for the integers. And this is the constant polynomials. Got it. Okay, so you just add 1 to the degree. Thanks. So this is now greater than or equal to 1. Equal to 1 when you have a constant polynomial. Okay? And if this is true, if, where's my Euclidean algorithm? Here it is. Then this is certainly true. Okay? So you need a size function that decreases when you divide. If you have that, I claim that everything that I've proved about the integers works. Namely, every ideal is principal, generated by the element in it of least size. Any ideal generated by 2 elements is generated by 1 element, which has this form, which gives the existence of greatest common divisors. If you have a notion of a prime element, and that's just an element such that any divisor, any factorization involves a unit, then you have the property 3 for primes, and then you have unique factorization in the ring into prime elements. So Euclidean rings are particularly nice rings, in particular because their ideal theory is so simple. And this would be a useless notion if the only 2 Euclidean rings that we knew were the integers and the polynomials over a field, because we could have done that without all of this abstraction. But what Gauss discovered was that he could prove that other rings, which were quite important, were Euclidean. So I'm going to give you an example. And then we might ask ourselves if every ring is Euclidean. Gauss. The ring of Gaussian integers is Euclidean with size function the absolute value. Delta of a plus bi is equal to a squared plus b squared. So that's the absolute value of a plus bi quantity squared. See, this is like an absolute value function, so we might try it for the Gaussian integers. Is that going to work? Okay, so let's see why that's true. And then a corollary of this, every ideal I is principal. So in particular, the ideal we constructed 2 weeks ago with z of I modulo that ideal isomorphic to z mod pz, p congruent to 1 mod 4, is generated by a single element, a plus bi. And once you have that, so this is the key statement. It's principal because it's Euclidean. That just is the statement 1. Every ideal is principal. And we constructed an ideal by constructing a specific homomorphism from this ring to z mod pz. The ideal was its kernel. So we now know it's principal generated by the single element a plus bi. And then it's not difficult to show that a squared plus b squared is equal to this prime p, which proves Fermat's theorem that any prime congruent to 1 mod 4 is the sum of 2 squares. And it was Gauss realized that to prove Fermat's theorem, you had to prove that every ideal of this ring was principal. You had to produce a specific element in the Gaussian integers that generated this ideal that was constructed abstractly. And to prove that every ideal was principal, he went back to the proof that every ideal was principal in the integers, and he imitated it. So let's see why this is a good Euclidean size function. So let's start with 2 Gaussian integers and try to divide one into the other. Okay? So if I have b and a, well, I've already used b and a. Let's call my Gaussian integers, let's call the Gaussian integers capital B and capital A so we don't confuse them with those two a and b in z of I. And we can write b as a times some w, where w is of the form alpha plus beta I, and alpha and beta are rational numbers. Well, all you have to do is see that you can divide a into b and get an expression like this, where, I mean, you can clearly do it in the complex numbers, and you have to see that alpha and beta are actually rational numbers. So that's easy because b over a as a complex number can also be written as b times a bar divided by a times a bar, right? And a times a bar is certainly a positive integer if a is something of this form. This is delta of a, right? So this is some positive integer. This product is in the Gaussian integers, so it's of the form an integer plus an integer times I. So if you divide that by a positive integer, you get a rational number plus a rational number times I. Yeah, Peter.
I just wanted to mention that you're never going to be able to prove that the size is 1 if only if the thing is a unit. Because you can always shift a size function. You can always add, 3 to a size
Of course. But if I did this, no. That's too good. That's a norm.
If you were evaluation, then
Yeah, I'm sorry. Thank you, Peter. Thank you. It's too good. In all the cases we're going to see, the size is 1 if it's a unit, but it's not true in general. Take that off. So we have this division. Now, we know that for a rational number, you can take its integer part. So write this number as, I'm going to erase this part here. But keep all that stuff up. So 0 is Euclidean algorithm. And that implies 1, which then implies 2, that then implies, where is 3? Oops. That implies 3, which then implies 4. Okay, now let's take this expression that we've written it as a rational number plus a rational number times I, and pull out the integral part of alpha and the integral part of beta, so we're left with a rational number between 0 and a half. Namely, if you think of the integers inside the rational numbers, if you have any rational number alpha here, you can go to the closest integer less than it, and then you have alpha 0 plus 1, and you have alpha as written as an integer plus something between 0 and 1. So do that. So write alpha is alpha 0 plus r0, and beta as beta 0 plus s0, where 0 is less than or equal to r0, s0 is less than 1. And alpha 0 and beta 0 are integers. And now multiply this expression out. So then we get b is equal to a times alpha 0 plus beta 0 times I plus a times r0 plus s0 times I. Okay? Now this number, this is going to be our Euclidean algorithm. We're going to call this number m, and we're going to call this number r. And I'm going to show you that delta of r, claim delta of r is actually less than half of delta of a. So I have this. I mean, it could be 0. Either r is equal to 0 or its size is small. Well, here I am using the fact that this absolute value on complex numbers is multiplicative, right? The absolute value of z times w squared is the absolute value of z squared times the absolute value of w squared. That's a nice property of the absolute value. So the absolute value of r here, delta r, is the same as delta of a times r0 squared plus s0 squared. Correct? But these numbers, whoops, I did something stupid. Back up, sorry. Bad mistake. I actually want these numbers to be, my fault, you can put them in any interval of size 1, so I want them to be between minus a half and a half. Okay, I can make sure if my alpha 0 is within 1/2 of alpha, good. If not, replace it by alpha 0 plus 1. One of these integers is within a half of the rational number alpha, right, in absolute value. So I can arrange that the remainders lie between minus a half and a half instead of 0 and 1. And then r0 squared plus s0 squared, this is less than or equal to delta a times a quarter plus a quarter, which is 1/2 of delta a. And I see that now I have to put less than or equal to here. Yeah. Stephanie. I couldn't care less. But you're right, you should specify 1. Let's do it that way. That makes it unique. Okay? Although it's not important for this proof. It's a good point. So notice how cool this is. I mean, if I could go to different rings, and I'm going to give you different rings where this thing is going to fail miserably. So for example, suppose instead of doing the Gaussian integers, which we've just proved is Euclidean by this property, we had tried a slightly more complicated subring of the complex numbers, which is this ring. Consider the following ring. Consider R, all of the things of the form A plus B square root of minus 5. So that ring would be denoted Z square root of minus 5. So this is like Z square root of minus 1. A plus B times the square root of minus 1. So you add things here by adding the A's and B's, and you multiply them by just using the fact that this number is a number whose square is is minus 5. Okay, now you might say, well, why don't we prove this ring is Euclidean? We could take delta of a plus b squared to minus 5 to be the square of its absolute value, just like we did for these complex numbers. And that would be a squared plus 5b squared. Right? But look how that fails over here. Even when we do this division, and you can do this division, and you write your quotient rational thing as an integer plus something between minus a half and a half, when you go here, you get delta of a, and not r0 plus s0 squared, but r0 plus 5s0 squared. And 5 times a quarter is 5/4. And this doesn't add up to a number less than 1 anymore. So your natural choice for a Euclidean size function on this ring fails. And in fact, this ring is not Euclidean. This doesn't work, at least in Gauss's proof. In fact, R is not Euclidean. You can't find a Euclidean algorithm in this ring for any size function. Let alone the absolute value squared. And the reason is that one of the properties that follows from being Euclidean fails. In particular, we'll see eventually that every ideal is not principal, but what I'll show you is that you don't have a unique factorization as the number 6 in R has 2 distinct factorizations. Namely, in this ring, you can write 6 as 2 times 3. Well, that's pretty easy. You could do that in the integers too. But you can also write it as 1 plus the square root of minus 5 times 1 minus the square root of minus 5. And it turns out that all 4 of the elements, 2, 3, 1 plus the square root of 5, and 1 minus the square root of 5, are primes in the ring. We have to show that. But in any case, this is 2, and 2 is not equal to this because it doesn't even divide it in this ring. See, if you tried to divide this number by 2, you'd get something which isn't in the ring. It wouldn't be of the form an integer plus an integer times the square root of minus 5. It would be a half plus a half, right? So because we have 2 different factorizations here, we couldn't possibly have any of these properties above it. In particular, there have to be ideals in this ring that aren't principal. So in fact, if you want to see an ideal that is in principle, if you take the ideal generated by 2 and 1 plus the square root of minus 5 is not principal. You'll find that R mod I, if I got this right, boy, I sure hope I got this right, Peter, is Z mod 2. Yeah, right, it's the ramified ideal above 2. Okay, so here's an ideal. It turns out the quotient is Z mod 2, and so it's the kernel of the homomorphism that takes a plus b squared to minus 5 to the number a plus b mod 2. So if you take this homomorphism from R to Z mod 2, you can check that that's a homomorphism of rings. It has a kernel I, which contains the number 2. And it also contains this number. That ideal is not principal. And so everything goes wrong. You can't have Euclidean ring here. Yes?
I don't understand why it doesn't bother us that R9 and S9 aren't.
Here? They're rational numbers. When I multiply them by this number A, they have to be in the ring. And the reason is B is in the ring, A and M are in the ring, so therefore B minus M times A is in the ring. So even though this number itself is not in the ring Z of I, it's in the ring Q of I because R0 and S0 are there. It's in the quotient field. But if you multiply it by the original Gaussian integer A, you have to get something which is in the ring. And then we calculate its delta by taking the product of the two deltas of these things that aren't in the ring. Because we can still take absolute value of any complex number. Okay? It's somehow this absolute value function is defined whether or not A and B are integers. And it's still multiplicative. Does that make sense? It's a little tricky. Good point. Yeah.
You need to show them that the product AR is less than UA.
Yeah, that's exactly what we're showing. This product, Emily, is what I'm calling R. So, yeah, the delta of R is delta of A times delta of this weird element. And this weird element is the thing that has delta less than a half. It obviously can't be in the ring because delta on the ring is at least 1.
And we know that delta is multiplicative.
Because the complex absolute value is multiplicative. See, this is a subring of the complex numbers. And that's the miracle that we're using here, that the absolute value of z times w is the absolute value of z times the absolute value of w. If we didn't know that, it would be much trickier to work with this function. Okay? So, some rings, we're going to have Euclidean algorithms, and all these nice properties are going to follow. And some rings, we're not going to have these properties, and we're not going to have a Euclidean algorithm, and et cetera, et cetera. So, the next thing you might ask yourself is, would it be possible to prove unique factorization, or everything following from 1? Could it be possible that is it possible that I could have every ideal principal without it being Euclidean? And the answer is yes. And is it also possible that I could have unique factorization without every ideal being principal? I mean, are these things actually stronger than each other? So let's make a little diagram, and then I'll make some remarks about where we're going. So we've shown the property R is Euclidean implies the property that R is what's called a principal ideal domain, which means every ideal is principal, for domains R. Principal ideal domain, every I is principal. Sometimes this is called a PID for short, principal ideal domain. And then that follows that you have a unique factorization into prime elements. We have to define what prime elements are possibly, but we have these implications, and we've already got several rings up here, Z, and polynomials over a field, and the Gaussian integers that satisfy this property, and so they have all the others. Okay. Now, what we're going to explore is the fact that you can have unique factorization in rings without having these two properties. So I'll try to give you an example of a ring which we're going to prove has unique factorization, which is not a principal ideal domain. So let me just talk about what prime elements are very briefly in abstract, what the visibility is in an abstract ring in terms of ideals, and then I'll give you an example of a ring where you have good factorization, but you don't have any of the first two properties. So let's rethink what divide means in terms. Rethink of divide, prime, all of our terminology in terms of ideals. First of all, what does it mean that A divides B in R? Well, that's if and only if B is some multiple of A, M in R, which is the same thing as saying that the B is in the principal ideal generated by A. Okay? Which is the same thing as saying that the principal ideal generated by B is contained in the principal ideal generated by A. So divides we can express in terms of containing of principal ideals. All right? We say it divides it properly if A is not a unit and if neither A nor M is a unit in R. So that means, so what that means is that means in this thing that B is properly contained but not equal to A, which is properly contained but not equal to R. See, this is the statement that M is not a unit. Because two ideals are equal, two principal ideals are equal if and only if both things are multiples of each other. If M is a unit, then A is also a multiple of B by M inverse. And that would say that not only is B contained in A, but A is contained in B, so they have to be equal. So the statement that B is properly contained in A is the statement that M is not a unit. The statement that A is properly contained in R is the statement that A is not a unit. So the ideal generated by A is not the same as the ideal generated by 1. So divisibility and proper divisibility can be expressed in terms of ideals. And finally, we say that P is a prime, or sometimes it's said is irreducible if you're talking about polynomials in R, if it's not a unit and it has no proper factor. If P is not a unit, P has no proper factor in R. Well, that's our notion of a prime number. Now let's re-express that in terms of ideals. That says that if you take the principal ideal generated by P, it's not a unit, so it's not equal to R, but, and this is the key thing, there are no principal ideals that sit between P and R. It's maximal with respect to principal ideals. Namely, you cannot find a factor strictly containing P which itself is not equal to R, because that would be a proper factor of P. So it says the prime elements are the ones where the principal ideal they generate is a proper ideal, but you cannot put any larger principal ideal between it and R. Okay? Now, if our ring is a PID, so that every ideal is principal, this is the statement that the principal ideal generated by P is maximal. So if R is a PID, then P is prime if and only if the ideal generated by P is a maximal ideal of R. Because any ideal between P and R would have to be principal. All ideals are principal, and we know P is maximal with respect to principal ideals. And that's the same thing as saying that R mod P is a field. Remember, we said that we could tell what maximal ideals were by the quotient. So we have a notion of what a prime is in a PID. It's the elements such that when you quotient out by their principal ideal, it's a field. Now, I claim that a general prime thing just means this is equivalent to R mod P is an integral domain. Right? Because if I had a proper factorization of P, P is M times Q. with neither p nor m nor q units or divisible by p, then in this quotient ring, I would have a product that was 0, namely m times q is 0, and that would force either m or q to be 0, because it's an integral domain, which would say that either m was a unit or q was a unit. So in the general ring, you can tell whether you have a prime element if the quotient by that principal ideal is an integral domain. If every ideal is principal, then the quotient by that has to be a field. Okay, now, that gives me a way of showing that there are rings that are not principal ideal domains. If I can write down elements where the quotient by that principal ideal is an integral domain which is not a field, then I must have other ideals. Okay, so I'm going to do that for you. So here's an example of a nice ring where we're going to show has unique factorization, nice theory of primes, but which is not a principal ideal domain. Example of a non-PID. Well, it's a second example. Namely, take the ring R to be polynomials in a variable over the integers. Now, take the ideal I to be the principal ideal generated by X. Now, this is a prime element. You can't factor X. I mean, it would have to be a polynomial of less degree, and if it was less the degree than that, it would be a constant, right? So this is, and in fact, R mod I is isomorphic, as you showed on the exam, to Z by the map that takes f of x to f of 0. And this is an integral domain. So that shows that x is prime in R because the quotient is an integral domain, but it also shows that this is not a principal ideal domain because this is not a field. And consequently, this cannot be a maximal ideal of R. Namely, it's maximal for being a principal ideal, but there are ideals that contain it in R. It's just that they're not principal ideals. Because since this is not a field, it'll itself have ideal theory, and by pulling back a non-trivial ideal from this, for example, the ideal, this contains the ideal 2 times Z, so we can pull back that ideal and take this ideal J, say generated by X and 2, where R mod J is just Z mod 2, namely it takes a polynomial, the homomorphism from R to R mod J just takes a polynomial f to f of 0, but taken mod 2. That's a bigger ideal than I, but the point is that it's not a principal ideal. Because if it were a principal ideal, I wouldn't be a prime, etc., etc., etc. So here, because we know that in general it's a domain, whereas in the case of a principal ideal domain, the quotient has to be a field, if we can ever find an ideal such that the quotient by that principal ideal is a domain which is not a field, then this thing is not PAD. Okay, but next time we're going to show that property 4 still holds for it. Namely, we still are going to be able to prove unique factorization into primes in this ring, even though it's not Euclidean and not every ideal is principal. We're still going to have a nice theory of factorization. So next time we're going to spend a lot of time on polynomials over the integers, which may be the most interesting ring of them all. So, see you then.